Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of E. coli. So each one is a different sequence, we have some features about sequences, and at the end we have the localization site of proteins in the sequence. We can get more information about it, the UCI machine learning repository, where it says this data contains protein localization sites. There was not very much information on the Kaggle dataset, so this is where I got the info. A bit more information on the features here. So we have a sequence name and then a number of different features generated from the sequences. Alright, so it's going to be a very simple notebook, but let's hop into it. I'm going to be using NumPy and Pandas for working with the data, and then we will use we're going to use PyPlot and Seaborn for visualization, and the train test split function and standard scalar from sklearn for pre-processing. Then also from sklearn we have our model, which will be logistic regression, and our confusion matrix, which is going to be used to analyze the results of the model. So let's go ahead and import all of that, and I can load in the data using pandas.readcsv. So we can get the file path up here. Here's the CSV file we want, so I'm copying the path, pasting it in, and we take a look. So, very simple data set, not very much data, but hopefully there are some good patterns in here that we can use to predict the site. If we take a look at data.info, you can see we have no missing values, which is good since we have so few examples, and 2 object columns. That would be the sequence name and the site which we're trying to predict. So we can start by pre-processing. I'm going to create a function called preprocess inputs, and right now all this function is going to do is take in a data frame. It's going to make a copy of that data frame, and then it's going to return the copy. So we're going to call x. The x will be the pre-processed version of the data. So you pass data in, get back x, and then x right now is just a copy of data, and now we can modify it in here. So I'd like to take a look at how many sequence names we have. I assume they're all unique. I just want to make sure. So I can type x subsequence name dot unique to get all the unique values, and then I can take the length of that to see how many we have. So 336 unique values, and we have 336 rows. So that confirms that each one of these is a unique identifier, in which case this column is not going to help us make our predictions. So we can drop this column with df.drop sequence name axis 1. So that's the column axis. And we're just going to say drop sequence name column. Alright, so we run this again. Oops. Then you can see the column is gone, and these are the remaining features. Now they're already encoded and in numerical form. So the last thing we have to do with it is scale the data. First, I'd like to split off the site though, because that's what we're trying to predict. So split df into x and y. Y is going to be what we're trying to predict. That's just going to be the site column. And then x is all the rest of the data that we're going to try to use to make the predictions with. So df.drop site from axis 1. Alright, and once we have split the data frame, we're going to do a train test split. So train test split, we'll use 70% of the data for the train set and the other 30% for the test set. So the train set will be x train and y train, and the test set will be x test and y test. And I'm using the train test split function from sklearn that takes in an x, a y. We specify a train size, and we include shuffle. This is on by default, but I'm just putting it there anyway. And since it shuffles the data first, we want to include a random state to ensure that the shuffle is always done in the same way. And so we're getting back 4 values now, and we're going to return those and get them back over here. So let's look at xtrain. So xtrain is only 70% of the data and no longer contains the labels, which are now contained in ytrain. And I want to look at ytrain a little closer. So let's look at our class distribution. Okay, so this is a bit problematic because we have classes in here that have only two examples, which is not nearly enough for the model to train on, because I guess there's three cases. One, all the this actually isn't the train set. Okay, what about the test set? Okay, you see we have classes in here that aren't even in the test set. So essentially we have these classes that we could never get accurate predictions on. So we should not really be trying to make these predictions, I think. It's a foolish task. So what we'll do is modify the task a little bit. And instead of trying to predict the exact protein localization site, we will change it so that we're trying to, we can say, simplify label target column. And what we can do is basically, let's look at value counts again. Can't type. Alright, so here is the CP, and you can see that this is pretty much, it's like more than half of all the others. So if we drop CP from here, and then add up all the rest, we get 137, which is just over 98. So we get a much better task if we're trying to predict CP versus other as our targets. So I'm going to do that. I'm going to take the site column, and I'm going to apply a function to it. Lambda function that takes in an x. X here will be a given site. And if x equals CP, then we'll leave x the way it is. And otherwise, we'll turn it into other. So after running this, x will either be CP or other. Then we only have two classes to worry about. So I'm going to store that in the original column, like that, and run this. Okay. So now our value counts are only 2, and this is a much more manageable task. Okay, so last thing I want to do is scale the data. So if we look at xtrain, if we want to look at the mean, you can see they're all, well, actually they have very similar means. I think it's because they all take on the same range, but they don't, they're not, okay, it's a little weird because if you look at, let's look at xtrain.describe. It's clear that these values are taking they're taking on values between 0 and 1, but you can see the min and max are not always 0 and 1 because 0 isn't always present and 1 isn't always present. So I want to scale it anyway so that they do take on the same range of values. So that we could do a min-max scale here, which is definitely possible. So why don't we try them both? I'll just import the min-max scaler along with it, along with the standard scaler. Standard scaler will just give each column a mean of 0 and a variance of 1. Okay, and we'll try scaling up here. So scale x. So we'll create our scaler here. I'll start with min-max, and we fit the scaler to just the train set because we sort of pretend we don't have access to the test set when we're doing this. And then we transform with scalar.transform the xtrain and store it back in xtrain. And we'll do the same thing for xtest. So we transform both data frames, but only using the fit to xtrain. Alright, and this actually returns a NumPy array, so if I return this, you'll see it's now not so nice to look at. So I'm going to turn them back into data frames after. I'll keep the indexes and column names the same as they were before. So xtrain.index and columns equals xtrain.columns. Now on the bottom it's going to be xtest instead. Okay, so now if we run this, we get back a data frame with the column names and the indices, so we're good to go. Alright, and if we look at this now, You see the min is 0 for all of the columns, and the max is 1 for all of the columns. So the min-max scalar either squishes or stretches the data so that the min and max lines up to 0 and 1 always. The means are still a bit all over the place, so it's a different kind of scaling than standard scalar. Standard scalar is usually better dealing with outliers, because if you have some bad outliers in this data, you can see, for example, in this one, we have a very low mean, even this one is even more, really close to 0, this mean, but the max is 1. So we probably had an outlier that squished all the data down to the really close to 0. So we'll see how this works. So, okay, now let's start training. So we're just going to use a simple logistic regression model. Logistic regression, and we'll fit the model to the train set. Then we can print out the test accuracy. So accuracy on the test set, I'll display it to 2 decimal places with the percent sign and format it as model.score xtest ytest. So the .score function for a classification model, like logistic regression, will return a accuracy value, and I want to multiply it by 100 since we want to display it as a percent. Alright, and we get an accuracy of 97%. So that's very good. Let's get a little better look at the data by creating a confusion matrix. So I'm going to create a set of predictions using model.predict on xtest. If we look at what this looks like, it's just the classes that it predicts for each example in xtest. And then we can call confusion matrix from sklearn to compare the test answers and the predictions, and we'll store that in CM. And then I want to plot the confusion matrix. So I'll create a new figure with figure size 4x4 using a seaborne heat map and passing in the confusion matrix, turning on annotations, setting the minimum color value to 0, giving it a color map of blues, and turning off the color bar. Alright, and then we can use, well, on the X we want predicted as the label. On the Y we want actual. And the title is confusion matrix. Alright, plot.show. Alright, so here's our confusion matrix. I can't actually see the class names, and I would like to. So let's find that with model.classes. That gives us the class names in order. So CP is 0 and other is 1. So we just plug that in. Oh, we'll actually create the X ticks. We'll set the tick marks on the heat map. So we have to specify the spacing of them first. That will be numpy.arange 2. So that will generate 2 values from 0 to 1, 0 and 1. And then we're going to add 0.5 to it to shift those spacing values from the corners into the centers of the boxes. And the actual values I want to pass in is model.classes. And I'm going to do exactly the same thing for the Y ticks. Alright, and here is our confusion matrix. So here's the CP class, here's the other class, and you can see these are the predicted values, and these are the actual values. So here, these are all the values we predicted as other. Here are all the values we predicted as CP. Here are all the actual values that were CP, and here are all the actual values that were other. And so these are the correct other classifications, and these are the correct CP classifications. Now it seems like we got one other wrong. We accidentally predicted an other as CP, and we got two CPs wrong. We predicted what was actually CP as other twice. So, I mean, we can't get too much better than this. This is quite nice. We have very little data, so to see a high accuracy like this is nice to see. I mean, it's nice. Last thing I'd like to do is try the other scalar. So instead of using a min-max scaler, I'm going to use a standard scaler. Like I said, this will give each column a mean of 0 and a variance of 1. Now you can see they don't no longer take values between 0 and 1. Their means are all extremely close to 0, and their variances, or standard deviations, which is square root of variance, are all extremely close to 1. Alright, so if we look now at this, we'll see if the results change at all. And we went up by about 1%. So if we plot this now, that 2 became a 1, and we now have only one misclassification for each category. Alright, and that was some of today's video. So it was a simple one, but thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.